Now, why do we care about thermal conductivity? Well, oftentimes we'd like to design materials that either spread heat very effectively, think about something like a copper skillet or a heat exchanger. In other cases, we'd like to design materials that are very good thermal insulators. So one of the best examples is a space shuttle tile. That's a little extreme. We also use thermal insulators in clothing, in designing buildings, in a lot of other cases, right? So these are kind of the two different extremes. Now, if you think about materials behavior, oftentimes we think about things that are good thermal conductors are also good electronic conductors. So metals, copper would be a great example, but that's not always true, right? So if we think about something like a diamond, diamonds are very wide bandgap semiconductors, so they don't conduct electricity very well. On the other hand, they're one of the best thermal conductors we know. So what's going on there, right? Why are diamonds good thermal conductivity, good thermal conductors as well as metals? And that's what we're going to talk about today. So first, let's think about the macroscopic description of thermal conductivity. Thermal conductivity is it's the relationship between heat flux and a temperature gradient. So just like diffusivity, just like current, we have some sort of a driving force. In this case, that driving force is the thermal gradient. And there's some sort of response. In this case, the response is how much heat is flowing. Thermal conductivity is the proportionality constant between that driving force and that response. So the higher the thermal conductivity, the more heat will flow for some given thermal gradient. How would we use this in solving an equation? Well, we could think about either steady state or transient thermal conduction type problems. If there's a steady state system, then the amount of heat that will be transferred per unit time, so this is the heat flux, is going to be proportional to the temperature gradient, dt dx, times the area, how much area is there for the heat to flow across, times that thermal conductivity. Okay, so what goes into the thermal conductivity? Again, we're just focusing on this proportionality constant. And it turns out that there are a couple main contributions, and we can think of them as being fairly additive. So there's an electronic contribution, and there's a contribution from what we call phonons. So let's talk about each of these individually. First, let's think about the electronic. And this is coming back to our intuition. We think about things, we think about metals as being good electrical conductors and good heat conductors. And in general, that's true. So if you plot up electrical conductivity and compare it to thermal conductivity in metals, you tend to see a fairly linear relationship. Now, and this is over many orders of magnitude. And so why is this? Well, it turns out that an individual electron is a good transporter of heat. So electrons can carry heat with them. So the more electrons that are flowing around in the system, the better the thermal conductivity as well. And so the gentleman, or the gentlemen who discovered this relationship got it named after them, essentially. So this is what we call the Wiedemann-Franz relationship. And basically it says that thermal conductivity and electrical conductivity are roughly proportional to each other. And that proportionality is L, which is the Lorentz factor, times the temperature of the system. So, okay, this part is fairly easy to understand. The more electrons, the easier the electrons can move around, the easier it is for thermal conduction to happen as well. But what about this other contribution? And now let me write this again. The total conductivity is the electrical plus the phonon contribution. So what is a phonon? A phonon is just a quantized lattice vibration. So if we think about our lattice, some crystal lattice, we've talked already about as I heat that lattice up, the atoms are going to start vibrating. Well, it turns out that they're not free to vibrate in any direction, just like electrons are not necessarily free to take any individual energy level that they please. Again, phonons are a quantized lattice vibration, and we can think about it as regular waves passing through a material. And so that's what we're trying to illustrate over here. So each phonon has some energy associated with it, and phonons can travel through materials like wave packets. Now the key thing here is that stiffer bonds tend to lead to higher phonon thermal conductivity. So if we think about something like that diamond example at the very beginning, even though the electronic contribution to thermal conductivity is quite small, there's a large phononic contribution. Okay, let's think about one other example, and this is something that's really counterintuitive and kind of weird. So if we think about a polymer, right? Single polymer molecule is a long chain. A macroscopic solid of polymers, if we think about something that's semicrystalline, we'll have crystalline regions, and then maybe they'll be surrounded by relatively amorphous regions of those polymers, right? So if I want to transport heat through this material, how does it have to be transferred? A lot of these bonds that I'm going to see are going to be the relatively weaker van der Waals secondary bonds between polymer chains, right? So if I'm flowing heat in this direction, for example, I'm looking at heat that's going from chain to chain. So these are those weaker secondary bonds. These are relatively weak, soft bonds, so heat does not flow very readily through them. If I think about just the backbone of a polymer, though, that's a pretty stiff covalent bond. So if I could design a way so that my polymers are all lined up so I could get the heat to flow just through that backbone, I could potentially have a polymer, which is a really good thermal conductor. And that's not what we think of, right? Most of the plastics, most of the engineering polymers that we think of are fairly poor thermal conductors. And so there was a group that tried this. They took a polymer and they drew it out to very, very thin, so nanoscale threads, essentially, of these polymers. And by doing that, they were able to align a lot of the polymer chains along the length of that fiber. So then, when they measured their thermal conductivity along the length of the fiber, they got thermal conductivities that were orders of magnitude higher than what we usually see in polymers. So again, the reason why is that we're thinking about thermal conductivity, we're thinking about the two contributions. The electrical contribution was still negligible, but in this case, I had a larger phonon contribution to thermal conductivity because I was able to line the polymer up so that it had heat conducting along these stiff backbones of the polymer molecules. Okay, so in summary, thermal conductivity, it has two main components. There's the electronic and the phonon contribution. If we think about the electronic contribution, we can get to what's called the Wiedemann-Franz relationship. And so this is just observing that as the electrical conductivity increases, the thermal conductivity also tends to increase. Finally, if we think about that phonon contribution, the stiff, strong bonds tend to have higher phonon-based thermal conductivities.